Hey guys, we're here with Sergio, who will be doing a talk on the key management landscape. I'll let him take it from here.
Hi. Hi, everyone. Every single one of your 2,860 viewers. Thank you, Shinju, for organizing this. I'm very impressed about the audience and the quality of the content today. And obviously, I'm honored to be here. So if here, check, perfect. Today we're talking about key management landscape and innovation. A brief introduction about myself. I'm an Italian entrepreneur. I've been living in Asia, Europe, and now in the US. I have been, I don't know, I don't think the echo comes from me. And I've been leading several internet startups. Most recently, I joined a company called Tangem, where we basically help the future of trust in the special world of asymmetric cryptography. At the end, I'll tell you also about the company, but I wanted to focus on our main topic today. So let's start from a brief history of key management. There's traces of cryptography from back in the history of times. Even the Egyptians had some sort of way to hide their findings. But the real notable trace is the Caesar cipher, where Julius Caesar was known to transmit proprietary and confidential messages by simply shifting 3 characters right or left in the alphabet, each single letter of the message. That was clearly easily breakable, but for his time it was already quite an advancement, and he was also known to be using a different type of shifting mechanisms. In fact, that was pretty much the best standard until the Vigenère cipher got famous. Although it was already described earlier in time, in the 1550s, by another Italian, Giovanni Battista Bellaso. And they used the same Julius Caesar cipher, but instead of shifting characters by a fixed amount for every letter, the amount was variable, depending on a secondary password, which would then be used cyclically all over the message. And this obviously was much harder to break, and it was only broken centuries later, a couple of centuries later, on a systematic way. In the meanwhile, coincidentally, this guy invented the one-time pad, because if we do extend this secondary password to the length of the message itself, or the clear text, then we have perfect cryptography, perfect non-breakable cryptography. It's called one-time pad. It was used later in history, the one-time pad, because clearly cannot be broken, but at the same time it's cumbersome, because big messages need a big password, and the password has to be shared beforehand, of course, so complicated. Mr. Kirchhoff later in 1883 became quite famous because he invented, or at least he figured out a lot of important things about cryptography. He published in 1883 a military cryptography manual, where he lists a set of principles. The most important that came to history are the second principle of cipher design, which states that the design of a system should not require secrecy, and compromise of the system should not inconvenience the correspondence. Let me translate this to you. The architecture of the system can be public, no problem. The identity of the speakers and the interlocutors can be public. Anything can be public. The only thing that has absolutely to be secret is the password, the secret key. If that stays secret, the system would work perfectly. And the fourth principle is that the cryptograms should be transmittable by telegraph. So similarly, At the time, the telegraph was the way to transmit data, and clearly you could not hide it. It was broadcasted to the ether. And so beautifully, he had already understood how you could speak in the public without being understood, which is what we're all trying to do these days with modern cryptography. There's a lot of evolution. Now things start to go fast, obviously, in the latest couple of centuries. The wars clearly sped up development of technologies on all fronts, including cryptography. And some of even the most famous battles, like the Midway battle, were won because of intercepted and decrypted messages. Then, of course, we all know the story of Alan Turing and the breaking of Enigma. German codes were broken a couple of times by the British, and the information was used in battle for a strategic advantage. Coming to the latest era of the last 50 years, things started to get a little more hot and complicated, and started growing exponentially complex. So the NIST decided to put everything together and establish a standard about cryptography. So in 1975, they established the data encryption standard as being the first of such standards. It was a symmetric standard. And for about 20 years, it was okay, until computation power grew, and these chips that you see on the left-hand side were able to break DES type cryptography in 1997 in only 56 hours. Of course, now it take a lot less, and there's also some open source projects for breaking it. Advanced encryption standards then were replacing DES in 2001. This guy here is Rindel, and he won an open competition where designs were promoted and evaluated. And this is the last bastion of symmetric cryptography. So today, AES is widely utilized, and it's to a certain extent secure as long as it's properly implemented. Of course, it's very secure as long as the data doesn't have to move around and the keys don't have to move around much. So the big next revolution in this respect is asymmetric cryptography. This is a very important step because everything that we see today, especially in blockchain, everything we talked about at this conference about decentralized finance, decentralized management, decentralized control, it's all based on keys being managed in an asymmetric cryptography system. Mm-hmm. The biggest milestone in this respect was the 1976 step by Diffie-Hellman. They published the New Directions in Cryptography, where they described how this system would allow for two actors to exchange keys and communicate in the public in a very secure fashion. Everyone has seen this diagram of Alice and Bob, where one key can decrypt and one can encrypt, and you can leave one key out in the wild and keep one for yourself, very safe and secure, and everything goes forward. The article, this publishing material, started stimulating a lot of discussions. So this is, remember, before AES. But there was already something brewing until it blew up in the 1990s, where the open source community and any cryptographers started to use the qualities of asymmetric cryptography. And it was okay until it was no longer okay. When in the 90s, the government started to grow unhappy about the use of asymmetric encryption for everyone. Specifically, the US government was forbidding export of technology, including cryptography. Phil Zimmerman, which is this guy in the picture, released publicly a system called Pretty Good Privacy, PGP, that is today still used for encrypting data and messages very efficiently. And eventually, all charges were dropped against him, and this system became a standard called OpenPGP, RFC 2440. If I may add some notes, whereas PGP is fantastically working, the reason why today it's not mainstream is that the user experience is not user-friendly. So there's a lot of people that can't access it because they are not familiar with managing their own keys. Three main points of managing keys are generation and storage. So the biggest challenge of someone's asking to put the slide full screen. I didn't see the immediate control, but if I'll find it, I'll let you know. The biggest components of double key cryptography today are generation and storage. And the big problem with asymmetric cryptography is that if you don't do it right, it immediately becomes very unsafe. So we've seen a few cases already in the past of cryptography gone wrong, and it all boils down to the classic tenet of security, which is a system is secure as its weakest link. So when we generate keys for asymmetric cryptography, we have one of three ways to do it. Either we use a pseudo-random number generation mechanism that will feed randomic number into an algorithm, which will then be utilized to compose the right type of key. Or we use a password, a user-given password, which can then be input into a key derivation function. Or we use a key agreement protocol in case you need multiple parties to agree on the generation mechanism of the keys. So this, for example, for the RSA key, what happens is that the random number generates two numbers, and a secondary algorithm checks, make sure that they're both prime numbers, and then it happens and multiplies them. Of course, it's a little more complex, but key generation can be wrong, and there were several instances where weak randomness in generation compromised a lot of systems. For example, at some point, a lot of SSL servers were generating keys just after spinning up a server instance in a specific structured data center. So all these servers had exactly the same image, exactly the same conditions. And so they were generating the same randomness. And so a lot of the SSL keys for multiple servers on the web were equal, which meant not only confusion, but also meant that any one of them could access all the others. So that was solved, obviously, with using better algorithms to create randomness before key generation. Another big step in key management is protection and storage. So I'll try now to get a little on the ground and make references to what the crypto world interfaces with keys on a daily basis. Once you got your key generated, then it's like a hot potato you got in your hands, you don't know what to put in. And And the best, one of the ways to do it is to do key wrapping. So you use another key, which could be also derived from a password, to encapsulate this first key. This is how usually the Bash SSL software works. That asks you for a password that uses to generate a key, that uses to encrypt your SSL keys. Another mechanism is on-the-fly generation from a password. It sounds similar to the first one, but you're not storing the key ever. So you don't have that hot potato, which is simpler because you don't have the attack surface of having a stored key on your system, on your phone, or on your server. But at the same time, it opens up to a new weakest link, which is the password that the user has chosen and generated. And we all know that usually we are not the best random number generators, and we tend to go for the path of least resistance and using passwords that are not safe, statistically speaking. Maybe of the 2,800 viewers, we are a selected audience that somewhat has been educated about picking the passwords, but mainstream, that's not the case. So we cannot really rely this on as a system. Or we can, third way, store the keys in a hardware token, like this one. Everyone's familiar with the YubiKey. So there's more than YubiKey. There's quite a few actually, but they all pretty much work in the same way. And I'll quickly skip to the token slide because this is interesting. So back in the days, the visual OTP tokens were the most popular. There's two types of visual OTP tokens. The ones that generate a number at every given time interval. And there's others that require an input first and then generate a visual number. And so this given number will be input into authentication login interface as a second factor. The challenges here are first in the subpar user experience in having to pick up the number, read it, wait until the time cycle is over, or input. It's a little bit of friction on the UX. But also there's a problem with over-the-shoulder visibility. So anyone could technically see what you're doing and read on your display while you're inputting your password. At some point, some devices were also helping impaired people by speaking aloud and enunciating aloud the number, which clearly makes it even more complex. The other two types of tokens are USB or insert or wireless. They're practically similar in the way they work, except the wireless one require, if they are Bluetooth, they require pairing initially. If they're NFC, instead they just require a tap on the NFC terminal or device or mobile phone they're being used with. The insert ones act as a keyboard. So the problem with the visual number giving tokens, the first type, is that you can only expect the user to type in 6 or 8 or 10 characters maximum, and also you introduce possibility of errors then. But when you do real asymmetric cryptography, the keys are usually much longer than that. And so the best way to have native asymmetric cryptography and proofs transiting on a system is to instead having one of the latter types, so the wireless or the USB type, that act as a keyboard and transmit a whole string of authentication characters all at once. The reason why these tokens are secure is that they solve two problems in one. They solve the generation and the storage. The two things we talked about earlier, generation and storage. And this is very important because we basically catch two birds with a stone. I mean, the device is not a stone. Hopefully it's never going to be break, but if they're properly designed and use proper standards, and there's alliances like the FIRE Alliance and others that certify these devices, the keys are really randomically generated, and they're properly stored in a secure element chip with various type of hardware protections against different type of attacks. And they are relatively easy to use, and in that it's a standardized system where there's interoperable protocols for using them. What if the keys instead are not in the hands of the users? What if you run a custodial service where you are managing the keys on behalf of users? Or what if you want to authenticate your users with a credential system where you need assigned credentials to be stored centrally or distributed, but anyway, not in the user hands? Well, in that case, you need to start thinking about a key lifecycle. And this can get really complicated really quickly. So I'll be somewhat short here, just because there's no end to this conversation. But the most important parts of the key life cycle are the creation and generation, which we talked already about. The storage at this point happens on a server. So you need all sort of protection because central key storage is a perfect honeypot. This is exactly where every hacker wants to go and find the maximum amount of return for their hacking investment. Then you have to think about activation. And activation can be part of the key creation and generation, or can be done at a later stage only after the key is delivered to the user. Key revocation is also an important part of the key management. Revocation doesn't necessarily mean deletion, but it means that the key shouldn't be accepted by the system. And also destruction and deletion is not always a definitive action, because sometimes there's a post-activation limbo where you put keys in escrow, and sometimes it should be used for later forensic analysis, or it can be used for being reactivated. For example, the deactivation can be temporary only, and the keys can be reactivated at a later stage. So all these mechanisms have, of course, to be hyper protected and are not very easy to get right in the first time. There's a few ways to do it, and usually there's platforms that take care of this scenario where you have a key management system. There you go. The hardware part is mostly done by a device called HSM as a hardware security module. A hardware security module is a small unit that is isolated from the operating system where it's hosted, and has properties of secure memory that is not accessible without authorization, and has the properties of safe key generation and storage and signing. So when a system requires a signature, instead of delivering key to a requester, it will sign on behalf, keep the key safe inside a secure memory, and only deliver a signature. So when you want to ask for a proof, a credential verification in a secure key management system, you don't get the key shuffled around from player to player. you will have a secure system called the hardware security module that will accept your request, sign what you need to sign with a desired key, return a signature, and never let the key out of the system itself. These are little devices that could be as small as a fingernail, and even YubiKey sells them online for I think $600 or $700, or up to thousands and thousands of dollars for very complicated solutions that are optimized for data center and optimized obviously for higher throughput traffic. Gemalto, for example, offers as a SafeNet system. When you need to set up a HSM platform with multiple HSM servers, the cost of the someone's asking about expensive hardware. Well, exactly, the cost is more operational because if you have requirements to have a centralized key management system with certain security standards, the challenge is not to buy 5 servers and put them in a rack, which may cost $10,000 or $20,000 or $30,000. The challenge is to keep the whole infrastructure secure. So access control to the location, the type of venue, the bandwidth, the type of personnel has to be authorized. And so you have a lot of paperwork type of complication that makes your operational costs grow tenfold, 100-fold, depending on what you are doing. Hosted HSMs, for that reason, are a thing where you can start delegating and outsourcing part of the systems. Virtual instances are interesting because just like we used to do on AWS, you can on demand click on, click off, and have various services start to stop as on demand. Centralized key storage seems like a bad idea, says one viewer. Yeah, of course, if you can decentralize it, you have certain advantages. But when you're a bank and you need to provision credit cards, and every credit card needs to be personalized with a key and a certificate, and that key has to be a symmetric key that is also stored in your payment processing center to authorize the payment transaction. You don't need a decentralized solution. You need the payment processing center to have the key to verify the authentication of the card. Similarly, SIM cards have KPI key provision infrastructure that goes back all the way to GSMA. So whenever you have a SIM card in your phone, now there's also eSIM and iSIMs, but the good old days when you had a little fingernail size SIM card, all those cards are provisioned with keys and certificates that have been issued, and the master keys are stored centrally somewhere in the GSMA servers. So there are situations where you really need to keep your keys in formats, and that's what HSMs and similar devices are for. So looking a little bit at the future now, of course, there's many other problems with the infrastructures around keys, but I want to focus a little bit on the users, because ultimately the whole point of decentralized finance and blockchain is to re-empower the users, to the citizens, to have access and control over their data, their finances, their assets in general. And I say assets because the most important aspect of asymmetric cryptography is that the underlying asset is irrelevant. We basically can decouple proving ownership and authentication from what's really behind it. So what's going to happen in the next 5 to 10 years is that identity and payments are going to converge into the same stream of authentication and key management mechanisms. We're already seeing some interesting developments with wallets that allow self-custody. This was not possible with old money, but with digital currencies, of course, cryptocurrencies first and a lot of other type of digital currencies, what we can finally do is have full self-custody. I own my key, I own my crypto. This means I need to know how to manage my keys. Otherwise, I can easily fall victim of my own ignorance. There's a lot of beautiful mobile wallets. And the pros and cons of mobile wallet solutions for self-custody is that they do empower anyone with a smartphone to manage their assets, but at the same time, they require educated, digitally literate person to have a relatively powerful smartphone that is charged, that has data connectivity, and with the proper apps installed, and that has also education about security and choosing the right password and who to give the password and not to give the password, who to give the phone and when to unlock the phone and give it to someone. So there's a lot of education that has to go in mainstream before we can safely say that the world is ready for digital currencies. And most importantly, because of convergence, we now also have identity that is coming in the same space. Self-sovereign identity is a very important movement, has started a few years ago, and now W3C has issued proper standards about verifiable credentials. We think it's a different world, identity, from finance, but it's not. It all goes back to key management, to proving ownership of an asset. Now, if your asset is a credential or an identity or an authorization for a login, or is a wallet on a Bitcoin blockchain, what's the difference really? So we have to be cognizant that we, 2,871 viewers now, are basically at the forefront of this revolution where we are shaping the next 10 years. And we can make it or break it, because if end users are not empowered with the right tools that protect them, but at the same time encourages them and incentivizes them to join the self-custody and join the proper self-ownership of assets, then things are not going to work. So I'll quickly cap this conversation with our history at Tangem and explain why it's related to key management. And also I'll make a quick announcement about a product that is fundamentally related to it, and also answer some of the questions that have been asked in a short while. Tangem has been working for 10 years on a solution that we call chip-to-chain, because it connects secure element chip directly to a blockchain asset. Of course, anywhere there's asymmetric cryptography, we can connect an asset directly to a chip. We create a certain type of smart cards that are readable with NFC. So for whoever can see my screen, all we cared about is to make the user experience very easy. Just tap the phone and see what your assets on the blockchain are. In this case, I have 0.03 Bitcoin in this card. And this is possible because we developed a firmware, and this is a real innovation, that uses a secure element as a processor. So we can compute crypto keys directly in the secure element, and we sign transactions, and we never let the keys out. This is exactly what HSMs do. So we basically provide handheld HSM at $15, $20 retail value for any user who wants to have self-custody of cryptographic assets. cryptocurrency now, but we're also working with identity and other interesting things. And also our SDK is open source, so any developer that wants to use our chips for key management, for cryptocurrencies, or for identity, or for anything else, they can just go on github.com/tangem, download SDK. We're soon going to provide also some bridges for a mobile framework, and build applications. So all our chips are interoperable, and they don't depend on our Tangem app. They can go on any app that uses our public SDK. And we support SecP 256K1, ED 2519, so we can interoperate with any type of blockchain possible. And now to the announcement. I'm very happy to say this because we've been working on it for a while. If any of you is familiar with wallet called Lobster, Lobster is a Stellar focused crypto wallet based on self-custody, so keep the keys in the phone. They have another product called Lobster Vault, which is a sister app to the Lobster wallet, and it empowers the creation of multi-sig structures for wallets on the app directly. Now they use a Tangem card as one of the co-signers. So this is the equivalent of a YubiKey for a blockchain asset without having the centralized FIDO Alliance certified infrastructure. So keys in your hand, completely decentralized, authenticating by tapping a card on the phone directly for as a co-signer of a wallet. And on the Vault app, you can establish as many signers as you want. You can build a whole M of N solution that you prefer. So this is a future where it has to be very easy for anyone to have a multi-sig solution without really understanding the workings of it, but having the power of an HSM in your hand. Just on a tap of a phone, you can unlock any type of blockchain asset and create the best compromise between security and user experience. Someone's asking what happens if you lose the card. Well, that's the whole point of doing a multi-sig wallet. If you lose a card, you reprovision another one and deprovision the first one. So you can do, KPI on your app. For the other Tangent card apps, Tangent cards, you don't want to lose it because the keys are only here and they cannot get out. Just like your wallet in your pocket. Do you have questions, or is my time up?
Your time is up, but if you just want to close and let them know how to reach you, that'd be great.
Yes, so my username here is Sergio Fly, which is also my Twitter handle, and my email address is sergio@tangem.com or hello@tangem.com. I'll read those emails too. Very happy to answer all your questions. Thanks for listening and for watching, and thank you, Shinji, for organizing this amazing conference.
Yeah, no problem. Thank you so much. It was a great talk. All right, we're going to go to our last session of the day now.